Okay, guys.
So you did by the time you think you can. What do you want?
Substitution reactions. Any questions about anything before we get started? Going once. Going twice. Okay. Substitution reactions, very important, very important. We had a general line reaction. Leaving group replaced by nucleophile. Okay? What's a good leaving group? What are good nucleophiles? Some of that is there. Possible mechanisms for this reaction. Okay. You might have a suggestion. Just magic?
Yep.
Okay. Magic? Okay. Well, that's not going to get us very far on quizzes and tests and other things. Let's see. Let's see. Well, the leaving group has to leave. Everybody agree? Leaving group has to leave this carbon. But what if it just leaves? What if it just leaves? Okay, I'm bonded to you, carbon. Bam! I'm taking my electrons and going. Can it do that? Yes. What does that arrow movement give?
A lone pair at the end.
That would give a carbon without the bond. There's two H's there. Two H's. 3 bonds total. That's a positive charge. Plus what? 3 lone pairs to begin with. If the bonding pair moves on to bromine, it becomes the 4th lone pair. So it would be what? That, and that's a minus. Guess what? We just made one product by that mechanistic step. What did we form here, though? Carbocation. What type?
Primary.
Primary. Okay, next step. What do we need to do? We need to make bond between nucleophile and carbon, can we? We got hydroxide, we got this. Should this maybe react? These electrons make bond there? What would that give? Yes, product. There we go. Both of them formed. How many steps in this reaction mechanism that we're proposing here? 2. What's the name of the 2 steps? What do you want to call the first step? Leaving group leaving? Yeah? What's a single word that can describe that? How about ionization? Did this thing convert to ions? Yes, ionization, leaving group leaving. That was the first thing we showed. What was the second step? What do you want to call it? I don't know if we can have a single word, but it would be nucleophilic addition to carbocation. Again, not a single word, but that's what happened, right? Which of these 2 steps is a rate determining step if this was the mechanism?
Carbocation.
Why carbocation
Slow step.
formation?
It's harder to...
Slow step. Let's do a reaction coordinate diagram, yeah? Type of energy, reaction progress. A, B, C. Some arbitrary level A. Where do you want to put C compared to A in terms of energy? Before we had maybe an alkene and the product was an alkane.
Higher.
pi bond was converted to sigma bond, stronger, more stable.
Come on.
This is sigma bond replaced by sigma bond. It's not as clear. It's not as easy to judge. You have to get out some bond string tables. I'm just going to put it pretty even. But importantly, where would we put B? Much higher, yes. Carbocation, charge, no octet. Okay, here we go, off we go. There's a transition state leading to this, right? Bond breaking. All right. Settle in here. Bond breaking took some energy. Now from here, nucleophile attacking, yeah? How much activation energy is that going to take?
Small.
Not much, we're falling downhill. Doesn't take much energy to fall downhill. Just a little bit to get things going, yeah? Maybe like that. I wish I'd drawn this even a little bit higher. Rate determining step.
A to B.
Carbocation formation. If that's rate determining, what do we call this next step in terms of rate? Fast step. Question. Of the two reactants, which ones are involved in the rate determining step? One of them or both of them? Only one. Which one is involved in the rate determining step? The alkyl halide, the alkyl bromide. Is the hydroxide involved in the rate determining step? No. Only one of them is involved in the rate determining step. That's why this mechanism I'm showing is called an SN1. Substitution by a nucleophile unimolecular, 1. That refers to the molecules that are involved in the rate determining step. Only one of them. That is a potential substitution mechanism by a nucleophile replacing the amine group. Do you like this mechanism? Do you like it, or would you rather see one that might be better for some reason? Do you like this?
Could you
Anything
rearrange
you don't like about this mechanism?
the primary carbocation?
Yes, thank you. Primary carbocations typically bad. We'd rather not form them. They're formed in mass spec because mass spec is a very high energy process. We typically like to avoid them in other places in our mechanisms. Secondary, okay. Tertiary, best. Resonance stabilized tertiary, wow, that'd be real good. Yeah? Primary carbocations, not great. Okay. What if this was secondary carbocation? What would that do to the energy of B?
Or reducing.
Lower it, right? And make this activation energy lower? What if we lowered this on down and down and down by stabilizing, by having a molecule where the intermediate was tertiary with resonance? Lower? Would that make the overall reaction faster than this reaction? Yes. How do you make this reaction faster? Which step do you focus on?
The rate determining step?
The rate determining step. That's what you want to improve. Yeah. Now we can't improve it here. Maybe we could, but moving lowering this down, well, it opens up a can of worms, but primary bad. Is there another way we could show this reaction, propose a different mechanism? How about down here? Anybody got a different mechanism we could show? By the way, before we move on, can a bromine just leave? Can a bromine just leave a carbon like we did, ionization? What if you put HBr in water? What happens? It ionizes? Really? What does it do? That leaves and you make H plus and Br minus? It ionizes. Did you ever question that in Gen Chem? When you showed that, you told it ionizes? It left the H. Can it leave a carbon? Yes, it can also leave a carbon. Yes. We showed it ionizing from a carbon. You've been doing ionization from an H since third grade. Okay? All right? Can we show a different mechanism? Anybody suggest something else? Alternative? Concerted? You've been doing some reading? Oh, come on. Yes, another way to do it. I'm just going to go ahead and show you. Another way is, tell me if this is reasonable. What if these electrons come in here and attack that carbon and kick that off? Is that possible? Regardless, what does my arrow movement give? What does my arrow movement give? It gives all that over there, yeah? Oxygen now bonded to carbon. And what does this arrow produce? Fourth lone pair moving on the bromine. The bond is broken. Br minus. There you go. All that together now is called what? A concerted process. Yes. Is this possible? First off, where's the carbocation?
There is one.
Oh, I didn't form one here. So you mentioned you don't like primary carbocations?
Correct.
I didn't form one here. You happy?
I'm unhappy. the first one will allow for rearrangement, right? Or no?
Allow for rearrangement. It sounds like you want rearrangement. What if you did not?
Well, then we would do SN2.
Well, I mean, I can keep going. What if your action wanted to do SN1 and you didn't want rearrangement? Then allow would not be the right word. It would be a problem.
Okay.
So it all depends on if you want it or not. Allow sounded like you wanted it. Sometimes you don't want it. Question?
For SN2, would stereochemistry matter?
Stereochemistry?
Yeah.
Yes, stereochemistry is going to matter. I cleaned my card off. I don't know why I did that. Because now I don't have a handout from 6 weeks ago where I showed you 2 different ways to make bonds to carbon.
From the back.
Please get that back out. That's what we're doing right here. Have you seen that before? Yes. We've done a lot of this before. Stereochemistry. What type of stereochemistry? What do you want to call this in terms of stereochemistry type of attack we just did? Backside, yes. All this will be the same because what I showed you, that page, I told you it will be very important to learn and be useful going forward. Okay? Yes. There you go. What can we say about this? Why would hydroxide do this? What kind of physics is here? That's minus. Is there any plus at this carbon?
Partial?
Yes, there's a dipole. There's a partial plus. It's not a carbocation. It's not a formal positive. But it does have a partial plus. Is this going to attack a carbocation faster or a partial plus faster? Which would it be attracted to more? Physics.
Carbocation.
Full plus. So maybe this is more difficult. That doesn't mean it can't happen. You know, maybe we have to heat it a little bit more. Okay? Partial plus, not a formal plus. There's no carbocation. When we looked at this before, backside attack. We can attack a carbon and kick off a leaving group. Yeah? So it ain't brand new. How many intermediates here? How many steps in this reaction? One altogether. It's concerted. There's no intermediate. Okay? Reaction coordinate diagram. If we call this A, there's no B. I'm just going to have to call it this B, but then the B. If I call this C, no matter way I do it, it's going to be a problem. I'm just going to call it B because it's the second thing. We went from A to what? B. What do we have here? Just a transition state, right? That's your activation energy. That's your transition state. This is your rate determining step. Which step is rate determining?
The only step.
That step. It's only one step. Question?
I had a question regarding the SM quantity. Why do we have any rearrangements with that H? Why do we have a hydration?
That's a good question. I just only did a mechanism for forming product shown. It's like when you were asked to show a mechanism. The goal is to show a mechanism for what's shown. I could have done a hydration rearrangement, but it wouldn't have given the product shown.
So would that have been a major product where this is the
Again, we're doing a mechanism here. We have the product.
Okay.
Okay? I'm approaching this as we're showing a mechanism.
Okay.
When I give you a mechanism on a quiz or test, the product shown may be a very minor product. It may be formed in 2% yield. But still it's formed, and we can propose a pathway to how it is formed. That's what we did. Yes, it could rearrange. We talked about that. Do you want it to? Do you not want it to? We'll come back to that. That's a potential problem. It's also a potential good thing if you want it to happen. Are we going to get any rearrangements in our next mechanism?
No.
No, you only get rearrangements with carbocations. I don't see a carbocation down here. So no potential. Okay? By the way, the two reaction coordinate diagrams we've drawn here, they were in the handout from test 2 with the various reaction coordinate diagrams. And I showed you this one on the last page. It said there's no intermediate, only a transition state. Okay? Okay, how many of the reactants are involved in the rate determining step here? Which is the rate determining step? That step. They both got to be involved. If they ain't involved in that step, then they ain't involved. Both of them are. That's why this is called an SN2. Two compounds, two reactants involved in the rate determining step. Substitution by a nucleophile. Bimolecular. Okay? Which mechanism do you like best for the example reaction here? SN2 is the one. Okay? Put an X over number 1. Put a check mark by number 2. Why? The main reason because number 1 is bad because you never want to form a primary carbocation. At least unless you have to. I mean, we may do it, but want to avoid it. 2 is the mechanism here. This is a classic example of an SN2, and the halide, primary halide, is going to react by a SN2 because it's not going to want to ionize. We said things can ionize. Yeah? If it's carbon, does it matter what type of carbon is formed here? You've got variation.
Yes.
Primary is not formed easily. Secondary is okay. Tertiary is best. So there's different types of carbons, okay? What else can we say here? Okay. Kinetics, we've already kind of talked about this. Kinetics have shown that the rate of the above reaction can be affected by changing the concentration of either the alkyl bromide or the hydroxide. That is, I'm just telling you number 2 is the best. Do you want me to just tell you, or would you write like some evidence, some data that supports that number 2 is the best? You want data? Okay, we can actually do rate data. We can go to the lab and study rates. We can't see the molecules moving, but we can see rates. And if you do that, the rates will tell you that the concentration, the rate can be affected by changing the concentration of either one of the substrates. That information tells you that both are involved in the rate determining step. Since both are involved in the rate determining step, this information tells you it's SN2. Because if it's SN1, will changing the concentration of the hydroxide change the rate?
No.
It will not. Why would it? Because up there, hydroxide is not involved in the rate determining step. Why would you expect if the concentration of the hydroxide changed, you would change the rate? It's not involved. But the information told us that both were relevant to the rate. That means it's SN2. So that's how you would prove it for. And I basically tell you that in writing there. What would be the rate equation for the SN2? Right here. Rate equals some type of constant times the concentration of both substrates. What if it was SN1? How would this differ? It would not involve that. It would just be some type of constant times the alkyl bromide. So hydroxide, the nucleophile is not involved in the SN1 rate determining step. But it is in the SN2, not in SN1. Which mechanism matches SN2? Okay, we did that. All right, so rate information, understanding that rate equation. Let's look at a next reaction. Somebody mentioned stereochemistry. Want to see an example with stereochemistry? I thought you did. Here we go. As you take this alkyl halide, reacted with hydroxide. Why on the previous page did I say OH minus, but here I said KOH? That's because if you got an OH minus, you got to have a plus, right? You can't go to the stockroom and say, just give me hydroxide. They're going to say, do you want potassium, sodium, lithium, magnesium? What flavor do you want? Okay? So, I'm just showing you an alternative way to show it. But when you look at that, you know that's hydroxide, right? Okay? This is organic chemistry. All right? Hydroxide. Potassium is a spectator ion. You learned that in Gen Chem. It sits in the bleachers and just watches. All right? So hydroxide. If you do this reaction, we know that you get S only. Stereochemistry, that's R. You get S only. This is the first example we've ever done where the reaction is enantioselective. We only get one enantiomer. Well, the reason why is because we started with only one enantiomer. But this is the first time we've ever gotten just one enantiomer. This reaction is known to give complete inversion of stereochemistry. Okay, we call this inversion. R to S, or S to R would be inversion. Questions about this? First off, back to mechanism. Is an SN1 mechanism more or less likely for this reaction compared to previous?
Less.
SN1 more or less likely?
Less.
More. Why do you say less likely? The previous one would have been a primary carbocation. SN1 involves making carbocation. If you make carbocation here, it would be secondary. Is that more likely or less likely than the previous example? More likely.
But with the SN1 reaction, you create a carbocation and it can attack from the front or the back. And in this case, we can only attack from the.
Okay.
From the.
You're right. Exactly right. my question sort of ignores stereochemistry. My question is really looking at that this is secondary. I understand that you might think stereochemistry because it was highlighted. The question is, okay. I should clarify my question. Based on solely the substitution of the alkyl halide. Yes. Let's get to a better question. Which mechanism does this stereochemical outcome support?
SN2.
Because when you do this reaction, you know you get S. You can tell that by maybe polarimetry. Yes, SN2. Why? Because SN2 we know occurs backside, and backside is going to lead to what? It will lead to inversion. I don't know that we've called it inversion before. We've not explained that. But we kind of saw it when we did a bromonium. We came in and that's how we got like transition bromine. We've sort of seen it, yes?
If you were to do SM1, could you form S or R?
Yes, let's look at that. If we did SN1, what would be the product?
Percent?
Yes, both. You need to get the handout out from test 2. Okay? 2 ways to make bonds to carbon. Yes. I wish I had it right here. Anybody got it? I mean, everything is right there. We've been looking at this for 6 weeks. And the reason I try to present that to you very general at that point is because we're going to use it forever. And you need to learn it generally. And I wish books would do that more, as opposed to just talking about it when needed. It's not something you talk about when needed. It's something you need to know all the time. Yes, if nucleophile attacks a carbocation, you're going to get both, right? Because carbocation is planar, how do you attack? Either side. Yes. Yes. Down here, nucleophile kicking off the leaving group. Isn't that what we're doing with SN2? Yes. Backside. It's all discussed here. Backside. Different ways to show inversion. Did I say it was called inversion here? No, probably not. But this is called inversion. Leaving group forward, now back. Well, nucleophile now back. All right? It's all inversion. Which mechanism does it support? Well, the evidence supports SN2. We apparently got inversion. How is inversion obtained? Because I don't think I showed it on that sheet. I just showed you. Let's get, how's it actually obtained? Well, here we go. This is the same molecule R. I just got it shown differently. I got the bromine in the plane. Same molecule. Hydroxide. Here's the carbon right there, yeah? This thing is swimming around. How's it go? Where's it going to attack?
From the front.
Leaving group is that way. How's the hydroxide going to come in? Backside. Which is better called what?
Less interaction.
Opposite side. We call it backside. Okay? The bromine is that way. The hydroxide comes in this way, right here. Right? Bromine is in the plane of the board, like that. Hydroxide comes in exactly back. And it's going to kick off the leaving group. But there's a transition state, okay? By the way, it's slipping between the methyl and the H. Coming through there. Got to make space for this to come through there, yeah? All right, what's it going to look like in the transition state? Let's see. draw that carbon. All right, that's sort of full mechanism, but isn't this bond making and isn't that bond breaking? As the bromine breaks, and as the hydroxide forms, sort of like that, this is going from no bond to a bond. What's in between no bond and a bond? Half a bond. This is going from a bond to no bond. What's between bond and no bond? So this is where the bond is breaking, this is where the bond is forming. The remaining groups are let's no. Sorry. Let's put the ethyl straight up. I'll put the methyl and the H down. These two groups are actually eclipsing right now. Okay? The methyl and the H. The H is forward. The methyl is back. Okay? When the hydroxide comes in, my head coming in, and attacks the carbon, these groups start going forward. But right now, they're eclipsing each other. They're supposed to be right in. Okay, if you look down, you don't see them. Okay. And this is the transition state, sometimes shown with like a double dagger up here in the corner. Also called, what's another name for transition state?
Intermediate.
Very good. I didn't think anybody would know that. Somebody said intermediate?
It's like
It's not intermediate, it's a transition state. This reaction has no intermediate. Activated complex. Is that written somewhere?
Yeah.
Is it? Okay. Because I don't expect you to know that term, but it is a term that's used. Okay. We get this transition state. Then what happens? Well, the bond fully breaks, and this fully forms. All that's going on. It fully forms, and what's it going to look like? Well, the hydroxide is here. These groups get pushed. Okay? The methyl and the ethyl are like that. Okay? And the leaving group is here. When this comes in, it pushes these groups like that. And they're kind of like this, eclipsing each other. But then when this group gets pushed off, these things actually come this way to make room for the new group. So they go from here. See, I can't bend my, it goes to that. And that's the inversion. And so now these groups are like this. And this bond, it doesn't matter how you draw it. Okay? It has free rotation. It does not matter. But now, the H is here. And the methyl's there. Okay? I mean, the methyl's back, but it's just positioned that way. This focuses on the methyl being back. When the group comes in, the methyl moves here, and it's straight back right in front of the H. It clips. But then the methyl ends up coming pushed this way. This way compared to the carbon. It's still back. It's just going from there to here. Okay? And the H too. The H is forward, but when it comes in, they move this way. And that is what is inversion. And this is analogous to an umbrella. Okay? This here, like an umbrella over your head. You ever seen an umbrella go like that? Okay? Yeah. If it gets caught in the wind and it gets pushed up, that's inversion, like an umbrella. But importantly, when it goes from down to up, it goes through a planar transition state before it goes up. That is it. This here actually looks like an sp2 carbon. If this is considered a p orbital, like a p orbital here, and the other three groups are trigonoplanar. And what type of bond angles do you expect here? Indeed they are, and this is sort of theory. It's known to be right here we have 109.5 degree bond angles around like the methyl and H. Right here, 120 degree around these three groups. The three groups who are on the carbon are in a trigonoplanar relationship, geometry. Then they go back to 109.5. The transition state is sp2-like in character. Trigonoplanar with this being like a p orbital. How do you like the transition state shown? That's the bond being being formed. This bond being broken. sp2-like. Bond angle is important. What type of bond angle do the groups have to achieve to do the reaction? They have to achieve a 120. This is sort of theory that's supported by lots of evidence, okay? Unless you have a better theory. If you do, we can develop it, write it, submit it for consideration. Right now, this is the best. Transition state requirements can affect reaction rates. Explain the following SN2 reaction rate difference. You take this alkyl bromide reacted with what? I minus. That's spectator ion, right? The I minus can act as a nucleophile and kick off the bromine. Okay? I'm not showing all the details here, but it's attacking and kicking it off. Transition state, relative rate of 1. But if you try to do this on the smaller ring, the rate becomes much slower. Why? Why? What? What does that have to do with, why would that affect the rate? Yes. What's the bond angle right here?
16.
Ninth grade geometry tells us it's 60 degrees. This right here, I'm not sure. I didn't pass ninth grade geometry. It's more like, it's larger. Everybody agree? Okay, larger. Which one is going to have an easier time achieving 120 degree bond angles for the transition state? The one that begins larger. Again, you got to be careful. There's more than just the atomic angle. The internuclei angle is 60. That doesn't mean the orbitals are 60. Okay. That's a tetrahedral carbon. It should be 109.5. The interatomic angle is certainly 60. The orbital angle is more closer to 109.5. Not exactly. It's still strained, and the orbitals, instead of the sigma bond interacting like this, good head to head, maybe they're interacting like this. Some head to head, but it's still kind of curved, because the ring won't allow it to do like this. Okay? So there's variation, but still, when it goes to the transition state, the angles around this carbon actually get bigger. That's going to have a tough time getting bigger. That's why it doesn't react as fast. Okay? So understanding the transition state helps us answer questions such as that. And we're focusing on the SN2 transition state. Next, let's look at reactivity of electrophiles. The electrophile is the thing with the leaving group. It's the thing that hydroxide will attack. Or some other nucleophile. SN2 rate. All of these compounds here are toxic. Those are much more toxic than this. Chlorine's a decent leaving group, not as good as bromine. We showed the rate of the halides. What's the best leaving group of the halides?
Iodine.
Iodine, previous page at the top. These are all toxic because they're all very reactive in SN2. Much more reactive than this. Why?
Resonance.
What?
Resonance.
What was it?
Resonance.
Resonance? No.
The charges of
What charge? I don't.
Is it because they're trying to
They react faster. We want to look at the rate determining state. Rate determining step, right? What is the rate determining step? It's only one step. So let's look at this. Let's look at that step closer. Well, we still have it on the board. I didn't erase it. What about those compounds would make that transition state even easier to achieve compared to the other one? First off, why did we say resonance?
Well, for the first one, the benzene ring, wouldn't it be? It's more stabilized if the chlorine leaves, so it's.
But if the chlorine leaves, then you make what?
You make a carbocation,
That's what I thought you were
Oh,
doing.
but it's
We're
SN2.
doing SN2,
so we don't have.
and
Right.
SN2 doesn't have a carbocation. So that's why I wonder why you say resonance. There's no carbocation formed here. Okay, what all these four have in common that this one doesn't have is a p orbital next door. This is the carbon that gets attacked. There's a p orbital next door. Okay? P orbital next door. P orbital next door. Two p orbitals next door. Only one of them really matters. Okay? Now, right here. It may be hard for you to put this in your notes, but here's a carbon next door. What if the carbon next door had a p orbital? You know, it had that other stuff. Here's the carbon that gets attacking. Next door there's a p orbital. What would you have going on here? The p orbital that sort of forms here interacts with a neighboring p orbital. And that is a good thing. It's a conjugation that's occurring in the transition state. And that's going to do what to the energy of the transition state?
Lower.
Lower it. I erased it here. Remember how we went from here to here? What if this energy was lowered? I go down to here. Don't draw this. Which reaction can be faster?
This bottom one.
The one that has it lowered, okay? The p orbital next door stabilizes the transition state. Okay? P orbital next door. So when this gets attacked by the nucleophile, Doesn't this kind of become a p orbital? We showed that right here. But guess what? P orbital next door, they interact and it stabilizes the. Does this one have a p orbital next door? No, it doesn't have that benefit, so it's not faster relatively. Okay? These are all very reactive in SN2. You get these in your body, they're going to react with the nucleophiles you have, like in your DNA, your proteins. You have nucleophiles all in your body, biochemicals. Okay? This is less reactive. It's also thus less toxic. It will react in an SN2, but not as readily. Thus not as toxic. This type of compound is actually used in medicine sometimes like an anesthetic. It's a gas, things like this, gases, maybe to numb the skin if you're going to do a dermatological procedure. Okay? It can be, you would never put this on somebody's skin. It's going to be too reactive, it's going to cause problem. Tear gas, no, okay. They're just too reactive. Why? Hopefully we explain why. Number 2, effective carbon substitution. Okay, you've got the outline here. I'm just moving ahead. What are we even doing? What is 1 and 2? Got E, right? Okay, so hopefully I don't have to tell you that the outlines are set up to provide you with all the information. All right. Number 2, effective carbon substitution at the site of nucleophilic attack. Look at the rates here. Methyl bromide reacts much faster in an SN2 than the primary halide. That's faster than secondary halide. And this is faster than tertiary halide, actually much faster. Basically here. Tertiary halides never do SN2 with tertiary halide. Okay? Never. They're too sterically crowded. Okay? Don't draw this. Doesn't it have to come in backside? And if hydroxide here comes in here, kicks that off, yeah? Just H's. What if these groups were something else? What if they were carbons with H's? All right? And now this is on a tertiary carbon, tertiary halide. Now the hydroxide wants to get in there and it's like, oh, forget it. Sterics, it can't get in there. It can't get back there. Okay? Substitution. All right? The more you put groups there, it blocks. This is called steric congestion, sterics. It's going to slow the reaction down. For tertiary halide, it slows it down so much that it's negligible. And we just say for us, so if you want a definitive answer, don't do it. Okay? Secondary, you can. What's best? Well, these over here. Which of these 4 is going to be the most toxic? First one, because it reacts so quickly. Okay? This will readily react with your DNA and proteins and everything. Okay? Methyl bromide is actually used as a fumigant in big warehouses to kill roaches and rodents. They'll go in there and just spray methyl bromide everywhere and seal it up. And a couple of days later, they go in, everything's dead. Okay? So reactive, it reacts with everything in your body. Less reactive. Question?
I figured it out.
Okay. What about SN1? Which would react faster in SN1? The trend is just the opposite, because SN1 involves forming what intermediate?
Carbocation.
Which is going to form carbocation easiest? Yes, the trend is just the opposite with SN1. Okay? Okay, some rate over here to show that. Okay. Tertiary, negligible. See the rate? Okay, guys, we'll be getting into second gear next time. We'll be moving through this handout. Please look ahead so you know where we're at. What's coming? We're going to look at each component of these reactions. Right now, we're looking at the thing with the leaving group. Then we'll look at the nucleophile. Then we'll look at other things. And we'll do more example reactions other than hydroxide. Question?
Does the conversion always